All right, so this first tutorial consists of a few steps to solve the Poisson problem. The Poisson problem, perhaps the simplest boundary value problem when we start talking about PDEs. The first step here imports a GUI, a graphical user interface. You see a window popping up, and all the visualization will appear on right here on this window. All the modules from NGSolve are imported by this command, and in particular, from the Netkin two-dimensional geometry, you import the unit square, which is just a geometry object. The geometry object here can generate a mesh. Okay, so it generated a mesh, and how do you know what the mesh is? You go here, and instead of geometry tab, you click on the mesh tab, and that gives you the mesh. Okay, you can change the mesh size. You can play with other parameters in the meshing if you like. The next step is to declare a finite element space on the mesh. Okay. So for the Poisson problem, we need the Lagrange finite element space, which is called H1 in NGSolve. This object is coming into the memory when you said from NGSolve import star. Okay. So here, now you have the finite element space in your workspace. You can query it using the Python documentation, and you find that this is derived from a class FE space. This is a base class for all finite element space, and you can see a lot of documentation here. Many of this will make more sense as we go along through the multiple tutorials. All right, now what do we do with this finite element space? We want to solve a problem. So we want to solve this Poisson problem. We set up the problem symbolically, and for that, this is the next cell where you see U and V being declared as trial and test functions. These are just symbolic objects. They don't have any memory to store the solution. You will not have the solution in one of these trial or test functions. GFU, or grid function, on the other hand, has memory to store vectors, and that's where the solution will be computed. Okay. There is another syntax which you might like better than writing so many words here. You could say U and V equals FES dot T and T. You need to know what T and T is. It's not the exploding kind. You know, it's the trial function and the test function. Okay. All right. Finally, the problem statement. For the Poisson problem, we put in a variational form, and then you have a gradient of U, gradient of V. U and V are the test and the trial functions. So this is how you write a variational formulation in NGSolve. Now, for those of you who've been using NGSolve previously, you might be familiar with some other way of writing this. But Joachim, inspired by Phoenix, has now changed, has now allowed us the possibility to do the DX. DX is if you query this object in Python's documentation, you will see that DX is an object of type differential symbol. But essentially, you can think of it as something that represents the integral of gradient of U dot gradient of V. The DX representing this volume integral. We'll see more of this later. The assemble, so this is just a prescription of the form. Assemble then puts together the sparse matrix corresponding to this bilinear form in the basis function, using the basis functions that NGSolve has in its implementation. Okay. Now you can ask how does the right-hand side look? The right-hand side is a linear form, whereas the left-hand side was a bilinear form. The linear form has some source term x, which is just a coefficient, which is just the coordinate function x. And once you've assembled it, the f has a vector, and you can print the vector. This is the right-hand side vector. In case you wanted to know what is the specific entry of the right-hand side vector after assembly, you can print out and check that. And of course, you can also print out the matrix and check out the matrix entries. Except you need to realize that this matrix is stored in the CSR format, so the printout would reflect that. Okay. And then solve the system. Solving the system it's just calling the inverse of the matrix here. The inverse of the matrix with some free dots, which we're going to see in quite some detail in another tutorial very shortly. It performs the inverse, removing certain boundary constraint nodes, and you have the solution on the window on the side. Okay. All right, and you can also ask to print the solution vector if you wanted to know how the coefficients in the basis expansion of the vector looks like. Okay. All right. Now, the Jupyter notebook that I'm running is not the only way to interact with NGSolve. You can put up all of these commands in one Python script, run the Python script on the terminal, Python 3, Poisson, and you will just run a Python program without any graphical user interface. You could, if you want the graphical user interface, then you, instead of Python 3, you put netgen and run on the command line the file name. Okay, and you could also, if you want to, if in the situation we are in, and you want to get a Python shell, then you can go in here and ask for a Python shell here, and a Python shell will pop up where the Jupyter notebook, in the terminal that Jupyter notebook started.